The biggest takeaway from this whole lesson is being able to use this equation and these values to predict spontaneity in different situations. Let's, before we start answering these questions, let's just think about this temperature here, and can it be negative? And it can't be, because this is an absolute temperature. Remember, we're using Kelvin. Kelvin is, its lowest temperature is 0. And so when we start thinking about the values that we plug in here, we know that this T is going to be a positive number. So when we're trying to figure out how the change in entropy here affects things and what sign it has, we don't have to worry about how the temperature would change that sign. So anyway, we're going to interpret this, and we'll talk about, we're basically comparing these two parts of what goes into making it spontaneous. In other words, remember, we want, when we subtract those, we want it to come out negative overall so that the reaction would be spontaneous. That's our goal. So in general, so let's look at the two parts. I'm going to erase that. So if a reaction is exothermic, is that more favorable? Well, if it's exothermic, this term is negative. So that would be good. It would help delta G be negative. Of course, that's not the only part. Which is more favorable, an increase or decrease in the system's entropy? So the entropy is this. And so we would want an increase. And so we can put those together and say that if we have both of those true, if this term is negative and the S is positive, then this will be negative overall. And so when you add them up, you'll end up with a negative number for sure. So if that's true, then it doesn't matter what the temperature is. The reaction will be spontaneous at all temperatures. But the thing is, depending on how these come out, what the signs of these two values are, the S and the H, changing this temperature can make this term more or less important. And so if this term is favorable, we can have a higher temperature to make it kind of dominate and make the overall reaction spontaneous. In other words, what we're going to do on here is if delta H is negative, so this term is negative, and delta S is negative. If delta S is negative, then this is positive overall. If that's true, then this term is favorable, but this one is not. And so to minimize the effect of this one, we need a low temperature. Okay, what if they're both positive? Well, if this number is positive, that's not helpful because we want it to be negative overall for spontaneity. But this term, the S is positive, that would make this whole part negative, which is favorable. So we need to maximize this part of the equation in order to overcome this unfavorable positive here. So I need a high temperature. Okay, so again, the temperature is used to kind of emphasize or de-emphasize this part of the equation. What if the change in enthalpy is positive, not favorable, and the S is negative? Well, if the S is negative, this whole part is positive. We would be adding two positive numbers, so there's no way that could be spontaneous. Let's look at an example where we're going to figure out what temperature something would be spontaneous. And so the first thing you would do would be you would take these thermodynamic values and figure out the change in entropy and change in enthalpy for the reaction. And we've done that so much, I'm not going to show it all, but I will put a note about how we did it. on these kinds of problems, it is good to carry extra digits. And again, I got those values by doing the summation like we've been doing. Okay. Let's just kind of note what's favorable or not. This number, is this endothermic or exothermic? Well, this is positive, so this is endo, and this is not favorable as far as spontaneity goes. But it has an increase in entropy, so that is favorable. And so if we think of our equation, what we're saying is that the entropy is favorable for spontaneity. This one is not. So we're going to need to have a temperature that will make this term larger so that overall it will come out negative. Before we plug into that equation, remember we have to watch our units because our enthalpies are in kilojoules and our entropies are in joules. So I'm going to convert this one to joules. Okay, and the mole is, actually the mole is assumed to be there. We can cancel that with the coefficients when we use them. So anyway, now we're going to plug in and see what we need to have to make it spontaneous. And so what is the kind of the turning point? What does this value has to be negative in order for it to be spontaneous? But where's the turning point for that? And it would be, it would go from spontaneous or non-spontaneous to spontaneous right when this number is 0. So what we want to do is we want this term to be negative, and so it's kind of like we're saying we want this part to be less than 0. So I'm putting in a 0 for my delta G and saying I want this to be less than that. And when we switch sides, this turns, so and this is in Kelvin. Okay, so that is the minimum temperature. It needs to be bigger than that or equal to that. That's the turning point to make that spontaneous.